Okay, so welcome everybody to the final talk in our the HBIAMP image analysis series, or kind of the pandemic series, so to speak. Um, After this, we'll be kind of open to suggestions if we want to have something covered. Maybe we'll, when things get back to normal, we can get something that's a little bit more hands-on. But for now, this will probably be the last in this series anyway. And we'll finish off with something that's a little bit more complex. I mean, we started off with basics of how image formation starts, how do we even get a good image, and following on from that, basic image analysis, how to get levels and cleaning up your images and then counting, and then co-localization. Then the last one was machine learning, and then this is what we're going to end up with. And this is definitely going to be a beginner's kind of crash course. We're not really going to teach you how to do this from scratch. That is very, very difficult to do in this short amount of time. My goal here is to basically show you that you have access to these tools right now, and it's pretty easy to play around with. How do you apply it to stuff that you already have, to data and images that you've already collected, and maybe possibly what you can do in the future if you decide that deep learning is something you want to apply to your images. So we're going to go over some basics just to compare it to what machine learning is, or where it sits in the hierarchy. The technological advances that has allowed deep learning to be incorporated more and more into everyday analyses. The basic concepts of neural networks and how that's used in deep learning. Transfer learning, which is a concept that has allowed deep learning to really push forward, especially for image recognition and features and analysis. And then finish off with basically how this applies to microscopy and image analysis in particular. And I'll show you some resources that are out there that you could use. And then I'll just finish off very quickly with some examples run in Fiji and ImageJ and in the cloud. So what is deep learning? It basically sits in a little bit of a hierarchy where artificial intelligence is the overarching kind of group, and within that there's machine learning, and then deep learning is actually a subset of machine learning. So artificial intelligence can be seen to be anything that basically enables machines to mimic or demonstrate human behavior. A good example of this is basically your home devices, your smart home devices like Alexa or Google Home, Nest. That's kind of AI, so to speak. Machine learning is a subset of AI, and it uses models to basically allow machines to learn and improve through its experience and data. An example of that is your spam detection in your email inbox. So basically, through experience, every time you get a spam email, you would click on "this is junk," and which relegates it to your spam folder. And basically, the more you do that, the more the spam filter learns, and eventually you won't see that type of email again because it'll go straight into your spam folder. Deep learning is a subset of machine learning where basically its network is, or the way that it works, it's inspired by our brain's kind of network of neurons and its multi-layered capabilities of thinking through a problem. And an example of that is some of those automatic translation devices you would have on your phone. Those apps have been fed a lot of data to learn things like if you were in a foreign country and you saw a sign, that you knew what it was. You point your phone to it, and then based on all of the data that's been collected, it can recognize just the language and the shape of the street sign. It tells you, I don't know, don't cross the road here, don't throw rocks, something like that. And that would be just a kind of a simple deep learning example. I'll go over machine learning to kind of just ease into deep learning. For those who weren't aware, Dr. David Elliott, our one of our colleagues, gave a really good talk. It wasn't well attended because for whatever reason, but it was really good. And basically, that link on the bottom there will let you see the YouTube recording of that. He gave a really good talk on machine learning with respect to its use in an open source program called Elastic, which is super cool and very, very easy to use. And really, everybody should be trying to use that, especially if you're doing segmenting and trying to do some measuring and counting of your images, especially if the traditional options don't work. Also, he went over some of the new machine learning tools that are in Amaris, which I know a lot of you use. So just check that out. It'll be in our archives there. So machine learning can basically be broadly categorized into three classes. Firstly, you would say would be unsupervised machine learning, where the data that you input would be unlabeled. And basically, when you do something like that, you're looking for clustering. You basically want to model your data to discover some groups to see if there's any groupings or patterns. Reinforcement learning is kind of sits in the middle there. And it's basically learns by reward and punishment. It's a feedback system that you keep training that model, tell it if it's right or wrong, get it better, or if it's getting worse, and hopefully it gets to the point where it's much more accurate. Supervised learning is when you input data that's already been labeled, and basically the models you're looking for acts as classifiers, so that it will eventually learn enough that it'll automatically label new data that comes in or predict future outcomes. And then, of course, you can have if your labels are not very discrete, then you can just have some regression to options there for the supervised learning. Pictorially, you can see kind of just what I've said. With machine learning, you have a certain amount of data that goes in. However, you need to basically someone needs to be able to go through the step of feature extraction to label everything, to find the features that you will be feeding into the classification system for machine learning, and then you get your output, that it's a car or not a car, for example. For deep learning, the feature extraction is folded into the classification network, and you can see the big difference there, although I tried to make it a big difference, but you need to have a lot more data to be able to do this. And that's kind of the main difference there. So side by side, the training data set, as I mentioned, you need to have a very, very large data set. In some cases, tens to hundreds and thousands of images to be able, if you're training from scratch. And I say that with that little asterisk there in deep learning, because I did mention something called transfer learning that may be able to circumvent this a little bit. Because of the large amount of data and the complexity of the networks that are involved to do the thinking for you, the computational power is obviously very high as opposed to machine learning. Feature selection, I mentioned that. You need to do feature selection in machine learning, but it's kind of folded into deep learning, which is a good thing. Well, it's a different thing. It's one of the pros, I guess, for deep learning. Kind of related to the computational power is the training time. So if you have 10,000, 100,000 of images, then it's going to take a long time to train that model. In deep learning, classifiers just refers to the parameter space. Basically, with machine learning, there you have a lot of parameters to play with, but you have full control. When something goes wrong, then you're able to diagnose and see where it broke down in the model. there are few parameter spaces in deep learning, very few, which is good in a way, but then bad because when something goes wrong, it's kind of hard to debug. I did mention that it's computationally intensive to run deep learning, and not 20 years ago it was very, very difficult. I remember doing something similar, and it required to daisy chain a bunch of crappy computers together just to get something done in a couple of days. So nowadays it's much, much easier because, well, if you want to put it very generally, it's just the price of computing has gone down, and that we've been able to take advantage of graphics processor cards, or GPUs. It's always been the case that GPUs have had many, the architecture of GPU cards is that it has many cores. And people were asking, like, why don't we use these cores to our advantage, as opposed to CPUs where, the cores are in the tens, not in the thousands, as in GPUs. And basically it took a lot of programming to be able to talk or utilize these cores. And now that we have them, it's easy to run these networks. In fact, there are cards out there that are made specifically for machine learning and deep learning. So that's pretty cool. And not only that, for every iteration or every generation of new cards that comes out for the same price, you get almost double the amount of cores, which is pretty cool. And then you have data storage. Obviously, with so much data that you're collecting, it was expensive to hold on to it. I remember I paid $30 for a gigabyte thumb drive, and now that will get you a terabyte. And then, of course, not just the price, but the movement into solid state drives that make accessing your data so much quicker as well, which all adds up. The workflow of deep learning, very simplistically, first you have your label data, as I mentioned, and then you would split it always into the training set or test set, and it's always split in favor of the training set. Not always 80-20, it could be 60-40, but that's the generalization. The training set's always larger. And then it goes to whatever learning algorithm that you've chosen, some artificial neural network, for example. And it would go through, and then basically it would train a particular model or classifier. And at that point, you want to have a threshold. You basically want to make sure that model is, if you give it a threshold of 95%, it has to reach that. And once it does reach that, then you basically continue tweaking and optimizing, and then then and only then you push it through your test or your test set, your evaluation set, and which is only seen once, never at all. The training set gets used many, many, many times to basically build that model. And you will hear the term epoch, EPOCH, which basically refers to one full training cycle on the entire data set. And you'll hear that because that's how you build a model. You basically go through many, many epochs. That's one of the parameter spaces that you have to use to build your deep learning network. If you want to see how, say for neural networks, as the name suggests, it mimics the neural networks in our brain. And if you put it very simplistically, the input would be, the similarities would be the dendrites, and that input put that data in, and then the nucleus would be the transfer function, just the bunch of maths there that basically push through your signal, and then you get your output through the axon onto the next dendrite, basically, and then it just kind of links up. Now, again, this is the original term for neural networks. Well, basically one node or one neuron was actually a perceptron, but because of the similarities, and it's cooler to call it a neural network. So basically, you have to realize, as the picture suggests, there's a lot of input that can come in, not just one, and many dendritic spines and processes, and then you have a lot of these to go through and then connect up with a bunch more dendrites. And what in the background, what really is seen is a schematic picture like this, but you never see it because there's just too much there, and it gets simplified to what I showed before. All the inputs that come in have their own weights. The transfer function has a bias on it, and that bias is just another weight. And then there'll be a mathematical function or a threshold that has to be realized before it gets pushed onto the new output. And that would be a simplification of what I just drew. And one of these is represented by one of these circles. So you have a bunch of inputs, bunch of nodes, gets pushed through a layer. These are usually the neural networks are organized into layers. You have the input layer, one or many hidden layers, and you have the output layer. And a lot of that is pushed through all of these different nodes, and they can get pretty complex. And different neural networks deal with the way they pass information through to the hidden layers. And one of these versions is called a convolutional neural network. I won't go into how the interconnected neurons differ from regular neural networks, but I wanted to highlight CNNs, or convolutional neural networks, because of the relevance to image analysis. So CNNs are basically a neural network where the connectivity pattern of the neurons were inspired by the organization of the animal visual cortex. And the CNNs perform classification tasks directly from the data, like the images, video, text, or sound, and it actually eliminates the need for manual feature extraction. It's very effective in finding patterns in these images, such as objects, faces, and scenes, and you can imagine how useful that is for microscopy, because you're looking for patterns in your data all the time. And quite importantly, CNNs can be trained for new tasks that allow you to build on pre-existing networks, and this goes into the transfer learning that I mentioned earlier. So, so the workflow, if you really simplify it down, a lot of data again. If this is your training from scratch, and you have your threshold, and you have a bunch of masks and augmentations and filters to do all the feature extraction, and then you pop out what your data is, if it's a car or a truck or a bicycle in this case. An expanded view of this is basically what happens in that little black box is a bunch of things, one of which is convolution, which, as I mentioned, puts through a bunch of filters and augmentations that basically activates certain features in the images. It relates to the fact that you don't need any feature selection. ReLU, or rectified linear unit, is basically a mathematical function that maps all negative values to 0 and passes through positive values, and this really helps push things along to carry up to the next layer, and you have combinations of which. Excuse me. Pooling is basically downsampling, reducing the number of parameters that the network needs to learn, which is why overall with everything here, it really lends itself to pushing the networks faster through quicker, especially for image analysis. The classification layer is part of it. That basically it's part of the output that gives you a bunch of vectors that have classes of probabilities, and basically how it's able to predict. I won't go into the rest of that. It's a little bit too much. Transfer learning is what I wanted to talk about. Because usually, as I mentioned, deep learning in its purest form, you need to feed it a lot of data to be able to successfully train a model. Transfer learning is a way in which you train, where you basically use a pre-existing model as a starting point to train a model for a similar task. And then you basically fine-tune that kind of hybrid model. And it makes things much faster and easier, obviously, than training a network from scratch. And because of this, you don't need that much data. Like I said, you basically piggyback onto a pre-existing model. And there are a lot of models out there now that you are able to use. And the key is you don't have to look for something exactly, similar to your model. Let's just say you're looking for to classify cars and trucks. You can actually use something like cats and dogs. And basically, I'll talk a bit about that. The bottom one is obvious. If you have a lot less data, then you'd reduce training time and compute resources. So training from scratch is the old way. It takes a long time, a lot of computational power, and a lot of data. You use your pre-trained network to begin with in transfer learning. As I mentioned, you can use cats and dogs, and you think, well, how is that similar at all? And it's actually very similar, because if you think about it, an image is an image, and how a model has been trained to differentiate between a cat and a dog is something to do with, say, size, edges, kind of features, something like that, and which is kind of the same as a car or a truck, right? It's kind of the size of the vehicle and the edges that defines what is a car and a truck. So basically, you have a pre-trained network from cats and dogs, and then you fine-tune the network weights, and you end up with a nice model for cars and trucks. To build onto that, there is a way of making this even quicker, where you use that pre-trained network to feed into a machine learning model. So if you remember right from the beginning, there was the difference between machine learning and deep learning was that you needed a feature classification step. Here, you would use that pre-trained CNN to act as a feature classification or feature extraction to feed a machine learning model. So this is actually one of the fastest ways to use a CNN. So what's required if you were doing this? If you wanted to do deep learning from scratch, as I mentioned, you need a lot of horsepower, you need a GPU, a good GPU, obviously a lot of RAM, and for most people with even newer laptops are able to do this. Gaming computers are great for this if you have the right kind of libraries to play with. But if you don't, there are options. You can do everything online. You can do cloud computing, basically using the resources and the servers from Google and Amazon. And I'll show you an example of that. Programming skills, well, you don't need to in this case, because I'm going to show you how you get around that. But obviously, it doesn't hurt. Not everyone has the option of going out there and learning a language from scratch. But especially when things go wrong, even if the code is hidden, and if you're able to go in there and leverage some knowledge on why something went wrong, or how you would basically play with or augment somebody else's code, an open source code, to make it more suitable to your experiment. Your data has to be large to begin with anyway. And you'll hear the term ground truth, basically real data. And that was what we were talking about in terms of labeled data. So if you want your model to be, good, correct, accurate, you need to be able to sit down and go through your data and label it in a way that you want that model to see. So it's almost like training a child or teaching a child something. You would do something for them in front of them, and then they would mimic you. And that's kind of how it works. So unfortunately, they'll have manual annotation, especially for something like segmenting cells and things like that. There are things now you can do that you don't have to sit down and do it yourself. But yeah, data augmentation was kind of the filtering, and it basically is a way to randomize your data and to make your model more robust. You run a bunch of transformations, and you want to make sure that the network is not too biased. The one thing about neural networks is that no matter what happens, it will give you a result, an output at the end, because you give it a threshold, it will push everything through. So you want to make sure that your model is trained accurately and well. Resources, well, if you were going to do this, you have to start with annotation. So as I did mention, you have your ground truth data. You don't have to sit there doing it manually yourself. There are a lot of tools. Of course, ImageJ and Fijia is out there with many tools within that for you to label your data. Slicer I haven't used. Polygon RNN++, long name, I came across, and it's pretty cool. Ironically, it actually uses neural networks to run, and it's labels all kinds of image data quite easily. And it's also a great example of transfer learning, because it was shown that it was built on, at least one of their engines, or one of their models was built on traffic data to recognize street signs and traffic lights and cars on the road. But it was used very successfully to label cells. So that's a good example of transfer learning. You have your data repositories. So if you're not sitting on a stash of data, basically there are repositories out there that have a lot of images that you can borrow, such as in the cell tracking challenge. There's a lot of people who have uploaded a bunch of data there. Kaggle, I think is I found just randomly like 20,000, a folder with 20,000 images of cats in there. So so you can find places that have all of these repositories. Deep learning software. If you're a neuroscientist, you probably would have heard of Python. It's a high-level learning language. It's being used more and more because of all of the libraries that are available, and all the packages that just slot right in. And of course, all of the drivers and the software that allows you to take advantage of graphic processor units as well. Good old MATLAB. MATLAB is not available to all, but within UFC, we have a site license to it, I think, at this point. I haven't last checked, but they propose, or they purport that you can run deep learning in 11 lines of code. That just means that you're just calling one of their toolboxes, but that's still pretty cool. And they've got very nice tutorials on how to run deep learning very easily as well. And then there's CAF. I haven't used CAF, but it's worth mentioning because it comes up quite a lot. User-friendly software. I will talk about Deep ImageJ, one of the plugins in ImageJ that you can use. You won't have to see a line of code. These two are more machine learning, but I have no doubt that it's probably going to move towards deep learning at some point. Commercial image analysis software like Avio and Arrivis, even some of the Olympus softwares is now starting to offer toolboxes that do deep learning. I've kind of drawn this little line here to show what's involved in Python. As I mentioned, at the language itself, then you have all these tools and packages that allow you to use it as an image analysis kind of methodology. And even there are some that run off Python that are pre-written and pre-compiled to run pretty easily to do deep learning. These are Cellpose and Stardist. Cellpose is a very nice website, cellpose.org, that you can go and check out to see how it segments. It's a segmenting deep learning algorithm, and it's very simple, very quick, so you can go check that out. Of course, when you want to make sure you have a development environment to write the code, and then the infrastructure to run it and to share the code, and I'll be talking about Colab in particular. Okay, so what are the tools available for microscopy and deep learning? There are quite a few, but I'll just focus on some of the more common ones. And so you have image restoration, where you can denoise noisy objects, do deconvolution and super resolution to some noisy or kind of crappy images. And for one, basically, well, this I'll talk about in the next slide. Then you have object detection, which is really super helpful for segmentation, because I know some of you out there have images that are very challenging to be able to segment because of the way that they are. And of course, these can work into one another. You can restore your image, make things a little bit easier when you go to segment. Then there's virtual staining, which is not that common, but it may be cool in the future because that really takes away the sample prep. So these are some of the examples. You have denoising with a model called noise to void, which actually uses pre-trained models to clean up images, and you don't need a bunch of your of ground truth data, or not that much of it anyway. That's noise to void. Then you have care, which is content-aware image restoration, that does a great job in pulling out details and features like this. So it's not just about making bad images better. You have to think about it in a way that it really affects your imaging experiment as well. So when you're sitting in front of the microscope, thinking about this, you think, okay, well, let's just say you have everything set up to do deep learning image restoration, and you have a very sensitive sample. Now, you don't want to be torching that sample to try and get something. Let's just say if you're doing traditional deconvolution, you need to do at least Nyquist sampling, very dense sampling, to be able to get the pixel density and then enough data for you to do deconvolution. But that, more often than not, ends up giving you the risk of photo bleaching your sample. And I mean, all bets are off as well if you try and do this on a live, sensitive sample. So what deep learning could eventually do is to allow you to take images much quicker, which with much lower resolution, with a little bit more noise. So it's much gentler on your sample and it's much quicker. And then you would feed it through some deep learning networks and you get something back in return. Now that seems a little bit dangerous, of course, because it was still trying to get organized in deep learning, and you want to make sure that it's going to work at the end. So, but this is probably the future, to be able to take less than ideal data, but know that you will have usable data at the end once you pass it through a network. Object detection, I did mention already. Very difficult in some instances, but deep learning is working towards maybe making this into a very common technique that you can push through. You do combo. I did mention combo models where you can denoise and segment all in one pass through, and then regular segmentation. You have your object detection in terms of virtual staining. So I did mention this could lead the way towards reducing sample prep time. Not just sample prep, but every time you stain and treat your sample, to be able to stain, you end up putting it through a bunch of dehydration steps and whatnot, and the tissue is not the same at that point. So being able to do this could mean that you get to see your tissue in a more realistic standpoint. So just going through this, of course, this is not an exhaustive list, but I just wanted to highlight the repositories and toolboxes that are available to people online with respect to microscopy and image analysis. So the first one is CSP Deep, and it's basically a nice little repository where all the toolboxes are in one place, or at least the ones that they've collected. And not only that, they show you what you can do or what you can do with your data. It goes through and talks about where the origins and how these algorithms work. So it's a pretty good one to check out. I'll jump to Bioimage Model Zoo, which is basically on the same lines. It's kind of like a library of repositories. It's still a work in progress because some of the links are dead, I found, but what it does different from CSP Deep is it allows you to test some of these models in the cloud with test data. So that's kind of pretty cool. DeepImageJ is a plugin for ImageJ and Fiji that is pretty cool in that you can run it from pre-existing models, bundled models that they have provided, or you can put in one of your own models that you've trained on some other platform. These all kind of work into one another. Zero cost DL for Mike, a bit of a mouthful there, is basically exploiting Google Colab, cloud computing. You're able to run pre-compiled, pre-existing code with pre-existing models, and they even give you example and test data for you to run these. So a lot of the testing options in bioimage actually use zero-cost DL. And furthermore, you can use this Google Colab zero-cost DL for Mike to build models in the cloud that you can then save and then feed into Deep Image J. So it's all kind of connected here. So cloud computing, well, I'll just focus on Google Colab at the moment. So as I did mention, I'll go through the example, but you just execute it cell by cell, and it reads like the Jupyter notebooks or something with a lot of markdowns, a lot of explanations. The code is hidden in the background, and you just run everything cell by cell for you to just kind of put in your parameters that you need. You can start with the examples that they have with their example data, and then, well, eventually you can just replace that with your own data if you wanted, and train your own model there. There are a lot of points in which you can play with the settings and parameters. You don't have to stick to defaults. And it runs just like a regular program, actually. And that I did mention that you can train your model in the cloud and then export it into Deep Image J. It'll be a Python a file type, and then it goes straight into Deep Image J. And there are a lot of tutorials for both zero cost DL for Mike and in Deep Image J. Both their websites have YouTube tutorials to show you how to do that. Limitations is it's linked to your Google Drive, which you get 15 gigabytes in total free, which is not really, it's not 15 gigabytes anymore, because if you have a Gmail account, it shares that. If you have Google Photos, it shares that. So you don't have much in there to begin with. So that is the limitation there, unless you have a premium subscription model. When you use their GPUs, they kind of assign you a GPU randomly. You never really get the same one twice. This doesn't really affect, well, I haven't seen it affect my my training times, but that's just something to keep in mind. There is a 12-hour use limit, and I have hit that limit. Every time you deal with volumes, anything other than 2D, things start to get a bit hairy, and the training times get a bit long. And of course, with larger sets as well, it takes longer to train. So if it takes longer than 12 hours, you're out of luck, unfortunately.
Sorry, Kelvin, can I just jump in with a question there?
Sure, I was just about to stop there for questions, actually. It's a good timing.
Okay, great. I was just wondering, so that 12-hour limit for training, that's with the Google free account. If you have one of like the paid ones like Google Professional Suite, is that limitation, 12-hour limitation, removed?
You know what? I'm not quite sure. Since I didn't have a premium model to test on, I don't know. I don't think so. I think it's still like a fair use policy thing more than anything else.
Okay.
But don't quote me on that. I mean, I'm just going to say that 12-hour limit stands because very few of us have the premium model for Google. So
yeah,
for most people, about 99% of people, the 12-hour limit stands.
Okay, cool. Did you want to stop for any questions now as well?
Sure. Do you see any questions?
Yeah, we had one other question come in from Jackie. Just asking, is it possible to overtrain and create artifacts?
Yes. There's always a way in which you can mess up your training, but there are ways in which you can play with the weights, some of the parameters that help circumvent this. The data augmentation step is pretty important. You also, when you do this, when you do training, there's always a step in which you evaluate how the model went, and there are plots, and it'll show in terms of errors and things like that to show whether or not there is any unfair biases that are involved. So there are steps that should be included or are included if this is written correctly that make sure that you have an accurate model. So yeah, there are fail safes and safeguards in place if it's all written correctly.
Okay, cool. Thanks for that. Are there any other questions out there at the moment? No, I think it's all good.
Okay. So we'll spend the rest of the time, and it's going to be very quick because I put live in inverted commas here because, you know, Murphy's Law, if I tried to do anything, because not 24 hours ago, Google Colab was down for a little bit. So that kind of freaked me out. And as good as cloud computing can be, it still takes a bit of time. Like I did mention, if I tried Stardust, the 3D version, and that broke the 12-hour limit. So I'm just going to do 2D for now, and I've pre-trained the model because that took about 2 hours. We don't want to sit here watching the model train. So I'll go and kind of walk you through that, and then I'll show you very simply how you would run DeepImageJ if you had it. There are better ways to, not better ways, but there are other ways in which you can be more robust in using the DeepImageJ plugin, but I'm just going through the simple kind of click, 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 how do we do this? So, okay, let me see if I can switch it to this. Okay, well, I may as well just show you some of the websites I talked about. CSP Deep was one. These are the available tools. What can I do with my data? If it loads, I found that this website's a little slow. So yeah, in terms of image restoration, you have all these examples that are built off either the CARE network or the noise to void, noise to noise, noise to void, object detection. Yeah, let's just say I want to do microtubules. You click on that. And the good news is that you can, for a lot of these, not all, but most of these, they give you a choice of whether or not you wanted to run this network in Python using whatever resources that you have, whether it be Jupyter notebooks or a local kernel. Or they also give you examples to run it in Fiji. So that's pretty cool. If you don't want to mess around with the programming, there is a way to do it straight in Fiji. What else is there? Is this the Bioimage Zoo? Yep, this is the Bioimage Zoo. Kind of same concept as CSP Deep, where it has all these models there for you to show to play with. There are models, there are applications, the notebooks in terms of if you wanted to run this in Jupyter or in Colab. You even have some data sets to play with. They have got some test data or example data that you can use to pre-train or just to run and test. And I did mention that you can test these. So some of these have, I don't know, let's try this guy. Well, you can see there's still a work in progress. Sometimes you'll see a little link to a Colab, and that just allows you to test it out in Colab. Well, okay, here. You can launch straight into Binder or Colab. So yeah, this is still a work in progress, but a good way to kind of test out some of the models before you even have to download everything, which is pretty cool. And then DeepImageJ. So DeepImageJ is not run off the website, obviously, but I just wanted to show you how it looks. You can have, you download the plugin, and I wanted to in case you wanted to try this yourself, I would highly recommend, instead of downloading it and manually putting the plugin in the plugins folder, to actually put it through the update site method, because then it makes sure that it has the latest version all the time. The bundle models are here. Then you download these models, unzip it, and put it into a new folder called models in your Fiji or ImageJ folder. So it's pretty simple. And then you would run it from there. So I'll show you that how that runs. Oh, this is just Polygon RNN. Okay, so Stardust. Okay, so this is it's kicked me out because it doesn't like idleness. It's going to make me check if I'm, oh, okay, it doesn't want me to check if I'm a robot. That's good. So you can see that this is kind of the way, it doesn't look like a bunch of code, although it is in the background. This is just some markup, some annotations. It talks you through, well, actually, I'll skip ahead a little bit. I wanted to show you the Zero Collab kind of homepage, which is on a GitHub website. It tells you the network and how it works, how you would go about it with the notebook training data set, and you get your results, some demonstrations on YouTube. Then you have all of these networks. So we were in Stardust 2D there, and I'll go back to it. It has the original papers, talks about what it does, and the cool thing is it also has links to example and training data sets. So you can start off with something even if you have nothing to begin with, and then you just pop open the code in, or the notebook in Colab. There is some stuff that are under beta testing, like the combined denoising and segmentation, that it's not quite ready, but you can always play and try around. So going back to this, it's very well annotated. It reads, very easily, tells you what it does, and even tutorial notebooks, tutorial videos, tells you how you should go through this, what are text cells, what are code cells. Here is actually the kind of the contents page of how you go through this notebook. Before you get started, it talks about how you should, well, if you're using their experimental data or their example data, it should all be properly organized. But to keep in mind, for this to be successful, you need to basically arrange your data and name your data in a certain way for this network to be able to understand your data or recognize it. So now you would see this at certain points. You see these little play symbols, and that's just how you run the GPU. I've already pre-run everything because some of it takes a bit of time. But this is where you hit to check that your GPU is connected. In this case, I have a Tesla P100 connected. And then the most important thing is, whoops, sorry, what happened there? Oh, it's back. The most important thing is to mount your Google Drive. And how you would run this is basically it would give you a code, and it will go off and authorize you. You have to authorize your Google Drive, and then you put an authorization code there, and then you hit enter. Remember to hit enter. It doesn't say it there. So, but once that is connected, you know what? I'm going to go ahead and do it because it's important to show. And there we go. It's connected, and you should be able to see it here. In this file menu, you'll see your G drive, and I've basically put everything in Colab notebooks, in particular the Stardust, and I've put everything in here. All my test images, all my training images, so make sure that it's all in there. So this is where you install all the Stardust code and dependencies that it needs. It'll just draw that from repositories. Red is errors, but that's not always a bad thing. Sometimes it just doesn't find something that doesn't necessarily need. Here it goes through all of the parameters of the training and talks about, say, the number of epochs. Obviously, you can just use default values, but it does explain to you exactly what each one of them does. So one of the things you can do is once you run all the way through and click all the way through, is that you can come back and play with these parameters and see how it influences your model building. Okay, and here we have just another very important thing is just to link your training images from your Google Drive to make sure that it's well connected. And after that, you can save your model. I did mention you can save your model and then bring it somewhere into Deep Image J to use. So you set the path for that. These are all the parameters. It shows you your training, like just a quick preview of some of your training data. So in this case, it's some cells here and then the mask. So you have your training source and your training target. So say the gold standard or your ground truth. So this has been, say, pre-annotated by someone manually to make sure that the model knows what it wants, what it needs, basically. The data augmentation step I did mention to kind of make your model more robust. I didn't do this because when I tried it, it broke. So maybe I did something wrong. I'm not sure, but you can see all the different transformations you could do to basically kind of make sure that your model is pretty robust. You can input a pre-trained model with with weights. I didn't have one, so I didn't use this cell. Then you basically hit and train the network. And this took, maybe 1-2 hours. So that's why I ran this previously. You can see all the epochs there. And once that's done, it goes through a few things. Then you can download the model from Google Drive. It basically at every step, just like every good microscopist or imaging experimentalist, you don't want to leave anything online if it disappears or it wasn't saved properly. Going back to one of the questions is basically how do you evaluate your model to see whether or not it was overtrained, whether or not it reached the threshold. And there are different ways in which you can evaluate your model. One of the ways is a loss function, comparing your training loss, which is an error after each epoch, with the validation loss. And this is just a plot of that. So there are different ways in which you can look at that. Error mapping and quality metrics estimation. I didn't choose to do this, but that's yet another way in which you can really look at how well your model was built. And then at this point is when you would feed your model the test set for predictions. So the unseen data set, which is the small quantity that you split off from the main data set, and that's my test images. So, and then you click through, and boom, this is, say, an example of what the model was able to do. So this deep learning network grabbed a random image and then segmented it, analyzed it, annotated it, and basically that should be as close, if not perfect, with how you would annotate it manually to begin with. So then that's it. It's pretty simple. And this is it goes through pretty quickly if you just use if you use the example data and just use the default values. But this is a good place for you to kind of see or learn how a deep learning network would work with images. How much time we have? Well, you know what? Let's just quickly look at the, this is the same thing. I'm not going to show you it's pretty much the same thing. This is noise to void, dependencies, blah, blah, blah. This one took a lot less time to train because I think it's, the premise is that noise to void doesn't need a bunch of paired images of noisy versus clean data. So this one was a bit quicker, and then the end result showed something like this. So hopefully it's not, I've got all my downloads there from my models. It shows that it's cleaned it up pretty quickly. So the last thing I'll show you before we end it off is DeepImageJ. Again, I've kind of pre-trained something. Well, I'll run it live because it doesn't take too long. So I'll have to drag everything here. It's not going to take too long. So if you've installed it correctly, the plugin should be here under DeepImageJ. You could explore the models that you have. You can build bundled models. I'm just going to run because it's the quickest thing to do here. I'll show you what explore is. I downloaded a bunch of the bundled models here, and you can just click through, choose, and it has information on each one there. So yeah, that's one way of doing it. You run on a test image. Even talks about the architecture. But here I'm going to run. Where are we here? I'm going to run a super res wide field DAPI super res network. Some pre-processing, post-processing, and then boom, click. This is running in the background. This shouldn't take too long because it's a low res image. Hopefully. And here we have the results. I will change this to cyan for comparative purposes. And let's just zoom in here. Let's say here. That's the original. And that's the super res done with deep learning. So, you know, it's just a quick example. You can do much better than that. I've skipped over a lot of steps. But, you know, you see how easy that was, obviously. So I'll run one more and then we'll call it. Well, not that. So just an example of how, well, this is not exactly an example of transfer learning, but I'm going to run something for microtubules, and this is mitochondria. It is not microtubules, but it even works for this. So I'm going to run care deconvolution for microtubules here. The way you learn with deep learning is basically just to mess around, just like everything else. So, well, it's running. Let's see if something turns out from this. And okay, it worked. It's split into two. I'm gonna undo this. So I guess this is the, where is the original? This is the original, and this is the deconvolved. So it did an okay job. Again, it's probably not ideal because I've used something for microtubules that was trained on microtubules on mitochondria. But so there you go. Yeah, so that's kind of it. I'm kind of running out of time now, so let me just open up back into the slideshow. So in conclusion, is it for you? At this point, it's more than likely overkill for what you need. Not saying that you should be afraid of it and you shouldn't even try, because it's definitely something that you'll see more and more often. And all you can do is try. And as I've shown you, there's so many different ways you can dive into this without knowing programming. And it still sometimes feels like a little bit of a black box, but if you read through those examples, you can see exactly what's happening at every step of the way. It's by far a lot easier to understand now, and a lot easier to run with cloud computing, allowing you to play with this without the resources that you normally need. Yeah, start online, use the pre-made packages and the pre-made bundled models, and then you go from there. And the good news is, as we've already seen, that a lot of the imaging companies, software companies, microscopy companies are already including machine learning and deep learning tools into their packages. So there will be a time where you will sit there and you're just running an example. In fact, Nikon has one that you just run denoise in AI straight away, and you can denoise your resonant images right there. So I mean, it's already happening. So it's not something that is too complicated if they make it a way that is more intuitive. So yeah, that was just a very quick kind of crash course on deep learning and how it revolves around how it compares to machine learning and how you could use it for microscopy. So yeah, that's it. There are no more webinars in this series, but we are always open to suggestions. If you wanted to, if we hear enough feedback on something that's been bugging a lot of people, then we may put something out there. I mean, the hope is that we're going to get back to normal relatively soon, but fingers crossed. And then in that case, we can run something a little bit more involved, perhaps showing you some examples while running a microscope. So yeah, that's it. Is it? So let's just see. Is there anybody has any questions?
Kelvin, thanks a lot for the talk. We've got a question from Nathan, who's asking how these deep learning algorithms compare to more simple 2D filtering methods, such as Fourier transforms or convolution with Gaussian kernels and so forth.
How it compares? Well, the performance it's going to be difficult to show. Like I said, it's probably a lot of overkill, and you could do something much simpler like that. Whereas, it's a known quantity when you run those simpler things like Fourier transform, because you know what you're getting. With deep learning, it could very well be a worse result unless you train it very, very well. So I couldn't, it's a little bit subjective to say what if one is better than the other. Deep learning has the potential to be the best, obviously. And the best way to get the best out of deep learning is to train a crap ton of data with your own data. Even though transfer learning is out there, I mean, you can try that first, but yeah, it all depends on how well you build that model. And the results will speak for themselves, really. But yeah.
Yeah, if I can add something here. So essentially, when you're using, say, a Gaussian filter to average, your Gaussian filter, depending on the kernel size, will affect both your signal and both your noise. So your signal is going to be greatly affected, and it's one operation at a time. Versus deep learning is might not affect your signal at all, but might just recognize the noise and eliminate it. So essentially, with deep learning, it learns from many features in your image. So not only that a noise is present there, but what is the shape of that noise, what is its intensity, and so on and so forth. So there's many parameters that comes into the deep learning model to eliminate the noise, versus the spatial filtering, where it's one parameters at a time that you test and see if it affects it.
Yeah, it's kind of like machine learning, deep learning. It looks at all of those 2D spatial parameters at once and sort of figures out what's relevant and so forth.
Yeah.
Okay, are there any more questions? No, I think that's it.
That's it. Well, as I mentioned, there's all our, well, not all of it, but most of our previous talks are in our archives. So you go onto our website and you click through, we'll have kind of all the recordings there. We'll make sure that most of them, well, all of them are up there as quickly as possible. We messed up our recordings on some of them, but we'll make sure that they're up there. And yeah, if you have any questions, obviously we can take them offline if you want to email them to us. So yeah, but that's about it.